Hello, class. Okay, so last time we talked about engines and refrigerators. And we dealt with both of those as kind of like theoretical devices. So basically an engine works when you have a difference in temperature. Energy wants to flow from hot to cold, and we can kind of intercept that energy and take some of it to turn it into work. However, engines are actually real things. And so I want to go over just real briefly, the basic idea behind how some of these engines work. So we're going to go start out by talking about a steam engine, because this was the first engine put to wide use. I think like in the Industrial Revolution, they started building trains, things like that. Those are steam engines. So I'm going to draw a PV diagram. And the working fluid for a steam engine is water. So it's nice and convenient. And actually I draw a dashed line here, where over to the left of this line, we have water, and over to the right we have steam. So again, it depends on the, like when we're going to have this phase change, depends on the temperature and also the pressure. So these dashed lines, and in between, in this region, we have water plus steam. So we start out with liquid water, and kind of like on this boundary between water and steam. So we've got liquid water, and the first thing we do is we pump it up to a very high pressure. Now it's water still, so it's not, normally if you increase the pressure, if you think like a gas, you compress it and the volume would change, but your water is basically incompressible. It takes an enormous amount of pressure to cause any significant volume change. So this is basically a vertical line. Okay, and then once we get here, we run it through a boiler. And again, this is just where it's in contact with a hot reservoir. So thinking like an old steam engine, you have people shoveling coal into a boiler. And so you run this water through it, and the water is going to absorb that. It's going to go through this phase change, turn into steam. So we're going to have very hot steam coming out the other end. And then we can run that through some device to convert that steam into power. Now, in the old days, steam engines are actually still in use. So I'm thinking of those old trains. I'm thinking that they probably use pistons to do that. They had that steam push a piston. I'd have to actually look a little more into that, but but nowadays what we would use for a steam engine, what we do use for a steam engine, is a turbine. So it's kind of like a fan. You have this high pressure steam go through it, and that causes it to spin. And we'll see later, when you can spin things, you can get electricity out of that. But in the old days, spinning, you could have it spin the tires. It wouldn't be connected directly to the tires or the wheels, but that's the idea. And then we run it through a condenser. So, we get it back into its liquid state and cool it off in the process. So here we would need a cold, like a cold reservoir, source of somewhere to dump this heat. And so this is the basic process of a steam engine. The modern one, basically if you have steam, you can it's a high pressure, and so it goes through that turbine, and it's converting that energy into the steam is doing work on the turbine, and turning that into actual rotational kinetic energy. So it has to have a hot reservoir to produce the steam in the first place, And then a condenser, we have to shed off that heat with contact with a cold reservoir. So yeah, if you picture an old train, the cold reservoir would just be the outside air. They might have a cooling system, or if you have like metal plates with a lot of area so they can more efficiently give off heat. And nowadays, one place steam turbines are used a lot is nuclear power. So basically, nuclear power, all you were using these nuclear reactions for is a source of heat to create steam. So we let something like uranium or plutonium decay and give off heat, and that creates a high pressure steam, which we can then run through a turbine. Okay, so again, a very important device historically and actually still used today. So a steam engine. Now, a very popular engine used today, the internal combustion engine. So, say we have a cylinder with a movable piston. And this piston is connected to something called a crankshaft. And say we started out by having this piston move up and compress gas. Okay, let's start out. We have some valves where we open a valve and put in gas. So say the piston's at the lowest point of its motion. It's going to move up and down. Say it starts out kind of at the lowest point of its motion. So I guess I'd have to draw it with this a little more vertical. So we put in the gas, and then we're going to compress it. So the piston's going to move up, compressing this gas. And then we have a spark plug that's going to ignite the gas. And that's going to force the piston down. And that's where the power comes from. So it goes up, compresses the gas and fuel, and then the spark lights it, forces the piston back down, and then you open a separate valve. And the piston goes up again and pushes all the gas and what's left of the burning mixture, pushes that out into your exhaust system, and then that leaves your car. And then so you're up at top, you've completed the exhaust cycle, got kind of cleared the cylinder, and then you close that valve, open the intake valve, pour more gas and air into it. Now, old-fashioned cars, probably before the 80s, I'm not sure when they changed this, it was a gradual process, but in the old days, what they used for this intake, where you get the gas and air into the cylinder so you can compress it and ignite it. They use something called a carburetor, where it's just based on the partial vacuum that's created when the piston moves down. So that gas expands and lowers the pressure, and that kind of sucks the air and the fuel into the cylinder. So if you look back at cars from like the 1960s, they were extremely powerful because we didn't care about the environment back then. We didn't know that all this exhaust was causing a problem. They even used leaded gasoline, which very bad for the environment. But yeah, they had extremely powerful cars back then, much more than most modern cars. However, they didn't go very fast, top speed. They accelerated very quickly, but when it came to high speed, even like just a generic car, like you could have a Kia maybe beat one in a high-speed race. And the reason is, at high speeds, the engine's working so hard, it's going up and down so fast, that there's not much time to get the fuel into the cylinder, and so they have kind of like a breathing problem. And so they lose a lot of efficiency at high speeds, where nowadays there's a fuel injector that actually injects the fuel into the cylinder, and so they can go much faster now. But not like it really matters, because even with those old carburetors, you could easily go faster than you're supposed to. So it's basically like a 4-cycle process. Now you might wonder, well, there's only power during one of these cycles, so how does it actually work? Like, what's causing it to continue? Like, how do you get it started? Well, you have a starting motor for that. You really old-fashioned cars, they actually crank them and to kind of store enough energy to get it started, but now we use an electric motor to get the cylinders pumping, and then until that's going fast enough to maintain the cycle. Again, like your engines, if you look at you have a tachometer where you can see the RPMs, revolutions per minute. Even if you're not going anywhere, you're just idling, it's probably around 1,000 RPMs. Your engine has to be going a certain speed to maintain, or to just continue operating. If you try to go too slow, it's not going to work. And so yeah, you're only producing power during one part of the cycle. So there's a couple ways that you can keep this engine going. One is just momentum itself. But that's aided by, like, let's look at a side view of a crankshaft. So let's say here's a crankshaft. And you have the pistons coming, or the rods coming from the pistons. They kind of go up and down and cause this crankshaft to rotate. And there's a flywheel on the crankshaft. Just because the irregular pulses coming from the cylinders would cause this kind of jerky motion. So this flywheel, just like a weighted wheel, that just keeps it going more smoothly. We learned conservation of angular momentum, or just the concept of moment of inertia, or rotational inertia. If you have a large mass rotating, it's not going to speed up or slow down too easily. So that's a much smoother ride. But also, you have more than you have typically. Modern cars usually have about 4 cylinders. So it's a 4-cycle engine, and you have 4 cylinders. They're just each going under a different cycle. So like one of them is always in that power phase. Older cars had 4, 6, or 8. Some cars like Lamborghinis or something might have 16 cylinders, but yeah, having at least 4 is nice. You have like one in each of the 4 cycles at a given time to keep things running more smoothly. Okay, now a diesel engine is very similar to an internal combustion engine. One problem with an internal combustion engine, well, there's, generally you want to make the engine as efficient as possible. And it really comes down to like how much you can compress that gas. That's a major factor. And internal combustion engines have a limit to compression. And remember, you put the air and fuel inside, and then you have the cylinder compress. And once it's compressed, you light a spark plug, and that pushes the cylinder down. The problem is when you're compressing this mixture, it's heating up. And so if you try to compress it too much, the compression is going to cause it to spark. To ignite. And you don't want it to ignite when it's going up and then force it back down. You want to time it right so it kind of gets to the top. The engineers figure out exactly when the optimal time to cause this spark occurs. But if you try to get too much compression out of an internal combustion engine, that'll be a problem. So a diesel engine works a little differently, where they just compress air and get that superheated. So you can compress the air a lot, get it superheated, and then you inject the fuel, and that's just going to automatically ignite because of the, it's already very hot. And so a diesel engine works, they don't have spark plugs. The details are a bit different, but otherwise it's the same kind of process. Diesel engines are actually very widely used, not as much in cars and trucks, although they do exist, obviously. But larger engines very often are diesel because you can get much higher compression ratio with them. Okay, now another kind of heat engine I want to talk about. This, just to go into something completely unusual, there's something called a Curie Pendle. Now this was named after Mary Curie. She was a famous physicist that worked with radiation back when it was first discovered. I think she discovered some elements, like one of the leading scientists at the time. And this is a very unusual type of engine. It's not an engine you'd ever build for any practical purposes. Just do it for fun. So let's say we have a simple pendulum where we have something made out of nickel. So nickel is just a metal. If you get an old Canadian nickel, They used to be made out of pure nickel, just like coppers used to be made out of pennies. But now, mainly thanks to inflation, these coins aren't worth nearly what they used to be, and they're definitely not worth as much as the metals that they're made out of. So, yeah, if you like old coins to find things like copper and nickel. Now, theoretically, any metal could work, but nickel turns out to have the right property we're looking for. Okay, now let's say we place a magnet over here. Just like an ordinary bar magnet or something. Now, magnets can attract certain metal objects, and nickel is one of those. So what's going to happen is a nickel is going to swing up here and connect itself to that magnet. Now, we're assuming the magnet's strong enough. And again, so we're causing motion to happen here. We can get work out of this. You could theoretically use this to power a device, but the engine we're talking about is extremely impractical. And again, right now what we have is we just have this thing lift up and slam into the magnet and stop. So, what's the point of this? It's a finite motion and then you're done. And all engines have to be based on like a cyclic process so we can continue getting work out of those. So here's where the heat part comes in. Now we're going to talk more about magnets later. Like what are magnets and how do they work? Ultimately, magnets kind of operate on an atomic level. You can think of every atom, you can think of it as kind of like a tiny magnet in itself. And so if matter is made out of magnetic things called atoms, so like this marker is made out of atoms that kind of act like tiny magnets themselves. So why doesn't this behave like a magnet? Well, the atoms are kind of randomly distributed. So it's like there's no organization between the atoms, typically speaking. And so magnetic fields are vectors. And so if you have them pointing in different directions, if you have a large number of them, they just cancel each other out. So how a magnet works, it's when you get them to kind of all line up. Think you have like all these magnets randomly oriented, and there's no overall effect. But if you can line them all up, then you have a magnet. So here we have, say, a permanent magnet, where the magnetic fields are always lined up, or like on an atomic level. Now in nickel, because it's in the magnetic field, this magnetic field tends to line up the atoms in the nickel, and so that makes this nickel magnetic as well, and then they're attracted to each other. Yeah, we're going to talk more about magnetism later. That's the basic idea. Okay, so we got this motion, and then it sticks to the magnet, and we want it to be a cyclic process. And you can think, what if we just like somehow pull the magnet apart and then release it, it'll do it again. But again, we have to do work in order to pull this magnet away, and it turns out we're going to do more work than we'd ever get out of it swinging back. So that's no good. So here's where the heat engine part comes in. So the nickel magnet here, well, magnetized nickel, let's say, is now connected to the magnet. And let's say we apply a flame. So we have fire. Now, kind of talk just real briefly about magnets, how it works with this kind of internal arrangement of atoms. They have to be arranged a certain way in order to get an overall magnetic effect. And heat is a randomizer. So the energy is absorbed, and we know that when atoms, like when an object absorbs energy, the atoms move around more. And so if you heat up an object enough, it can't maintain this organization and it loses its magnetic properties. And that's why nickel is a good metal to use here, because nickel will lose its magnetism at a relatively low temperature. Still, I think it's a few hundred degrees Celsius, so you have to heat this up quite a bit. But then, so it's going to swing up here, and then it's going to start warming up, and eventually it's going to get hot enough that it loses its magnetism, and it's going to swing back down. But now that it's down here, it's not exposed to the source of the heat. You know, you have like picture a small flame here, and so now it's going to cool off. So it's like this is our hot reservoir, that's our cold reservoir. So anyways, now it's going to cool off, and that's going to allow it to become remagnetized, and it's going to swing up again. and then it'll heat up and cool off and swing down. So this hot and cold, the exchange of heat, like absorbing heat from a hot reservoir and then shedding off that heat in a cold reservoir, this is a heat engine. It's a very strange one, but like everything we talk about with heat engines, it applies here. So yeah, like all different types. I guess you could consider something like a windmill a heat engine as well, because wind flows because there's a difference in temperature. And so you could put a windmill there to take advantage of that. So that previous lecture on just looking at engines as kind of a theoretical thing, if you're an engineer, you're designing an engine, you have to look at like all these factors, but the previous lecture, that's just very general stuff that all heat engines have to obey. So, huge variety. So it's really interesting that we have some kind of general properties. Conservation of energy, that's not too surprising. We should always expect that. But that idea that there's like a maximum efficiency for any heat engine, that just depends on the difference in temperature. That's kind of a pretty amazing result. Now, I also want to briefly talk about a refrigerator. So, kind of the reverse of an engine. So, a refrigerator works this basic property called throttling. So, say we have a fluid or a gas. Let's say a gas. Well, that is a fluid. And it's flowing through a, let's say we have a high pressure gas. And we force it through this narrow constriction. Now what's going to happen is, it's going to be moving relatively slow here and a lot faster here. And due to something called Bernoulli's principle, which is something we don't really talk about in this sequence, because that's in chapter 11, which we skip. But the higher velocity gas means it's going to lower the pressure. And what happens if you lower the pressure? I'm sorry, not a gas. First, let's start out in a fluid state. Okay, so then when we run the gas through this narrower tube, this is called a throttling process, and the device that does this is called a throttler. This has a significant decrease in pressure. So yeah, remember the boiling point and the freezing point of a substance depend on the pressure. So you've got this fluid, say a liquid, and when you drop the pressure enough, it can vaporize. And so you start out with liquid. Now we don't completely vaporize this. We have a mixture of liquid. Sorry, I keep saying liquid. Keep mixing up liquid and fluid. But we have a mixture of liquid and vapor. They use a particular type of fluid for this. They used to use Freon, but that completely destroys the ozone layer. So thankfully they stopped using that. So they've got a non-chlorinated fluid that much better for the environment. And now it's a mixture. Oh yeah, and so this evaporation process, this cools it off. So now it's a cold liquid mixture. Liquid and vapor mixture. And so this is what kind of goes, let's say that you open the door of your refrigerator. So like you're looking in the refrigerator and there's these coils that carry that fluid. So we've got this cold fluid coming in. This cold mixture coming in. And now this is colder than the interior of the refrigerator, so heat is flowing into this fluid, this mixture of liquid and vapor. And now that's why it's important we didn't completely vaporize it, because it's in that mixed state, so that heat that's flowing in is just causing a phase change. So it doesn't warm up the fluid. It's just turning more and more into vapor. And so it can go through, and again, it goes through this wandering process where it'll take a while to go through, and it's absorbing heat the whole time, and that's what keeps the interior of the refrigerator or freezer. The only difference is the temperature you get to. So yeah, that's how you keep the interior cool. But we're not done though, because we have to have a cyclic process. We don't just have a container of fluid and then we send it through and then discard it and just go through all the fluid. We want to have a cyclic process. So basically what we have to do is get it back into its liquid state. And so we do that with something called a compressor. So again, this just takes this fluid and compresses it. So the name kind of implies. Now the problem is when you compress things, you heat them up. So now we're back to a fluid state at the right pressure, back here, like when we started by putting in this high pressure liquid. So we're back to the right pressure, but now we've got the temperature is too high. So we have to cool this. So again, I can basically keep this picture. If you look on the back of the refrigerator, we've got, again, this coil that just does this. And so, again, it makes it go through this kind of meandering process where it goes back and forth. And again, this is in contact, this is like outside the refrigerator, so this is exposed to the room. And so, it starts out, it's very hot, and now it's going to start shedding off that heat into the colder environment. And eventually, it'll, be back to its initial state where we get it, where it's still at a high pressure, but the right temperature. So we run it through the throttler, which is where the cooling occurs. And, then we have a cyclic process. So again, we need this, it has to work with these differences in temperature. Like we have to be able to shed that excess heat. And this is another thing, like say your air conditioner breaks down. So say it's summertime and the air conditioner stops working. So you get a brilliant idea. So you're going to just buy a refrigerator, plug it in and just hold open the door. So you're cooling, you normally create all this cool air in your refrigerator. You just open that up and let all that cold air into your room. That way you don't have to buy an air conditioner. So actually an air conditioner would be cheaper. So that's not the best idea. But it's also a bad idea because it doesn't work. That refrigerator would actually heat up the room. So even though you're getting this cold air inside, remember it's shedding heat. You have to have this process where you shed that extra heat you got from the compression. So you'd wind up, if you did this, you'd wind up heating up your room even more. Okay, so lots of different types. Maybe I should talk about one more, but I'd have to read up a little bit on how they work precisely. But another really important kind of device would be, our source of energy would be geothermal. So if you dig a hole in the ground, as you go deeper, the things heat up. If you go deep enough, you get down to magma, so very hot. And so you have like the ground level, which is relatively cool, hot source underground, and you can actually get energy out of that. And I think they might have even built something like this in the ocean. So you have the surface of the ocean, you've got sunlight hitting it, the surface is relatively warm. If you go deep under the ocean, the temperature is cooler. It's not that much cooler, but again, you can get a flow of heat from hot to cold, and so you can build these things and just put them in the ocean and generate energy. I'd have to look into exactly how those things work. So I've read about them, but like what's actually going on inside, I don't know. So maybe I'll look into that and make another video just about that. But I think for now, just different types. Out of these, I think like the internal engine is a little different because something like a steam engine, or there's another type of engine called a Stirling engine, where you just have this fluid that's just continuously recycled, kind of like in this refrigerator. You just have this fluid that's a working medium for this exchange of like the heating and cooling. And it's just recycled through. There's something called the Throttling engine that does the same thing. The internal combustion engine is a little bit different because you're like putting in gas and lighting it. And that's kind of like most of the engine we've talked about. It's like a steam engine. You have water and you have a source of fire and you run this water in pipes through this very hot area and it absorbs that heat. And so, internal combustion is a little different in that you're actually igniting it. But that's equivalent to absorbing heat from the environment. It goes through that phase where it heats up. So the internal combustion engine is a little different. You have this intake and then this exhaust thing. Throttling engine, though, that just has this completely enclosed thing, so it works purely on heat. You apply a source of heat, and that can power an engine. There's some interesting videos where you can actually see this in action. I think I'll actually post one of those just so you can see it. So that's another type of interesting engine, which I didn't go into detail here, but yeah, there's a lot of different ways of doing it. There's actually even a different type of internal combustion engine. I think it's called a rotary engine. They're not used very often, but I think there have been a few cars built where instead of a piston moving up and down, you have this particular shape chamber, and again, I'm not drawing this very accurately, but you have this thing that can kind of move around in a complicated way inside, and at some parts it's like compressing whatever is inside, and some parts it's expanded just due to this kind of weird motion. Maybe I can find an example of that as well online. I'm not drawing a good picture of it. But I think there were actually cars built using that as well. So just tons of different kinds of engines. But generally, if you have a difference in temperature, you can get something useful out of it. So lots of different means of doing that. That's why I wanted to include that Curie pendulum. It's just like a crazy thing. But it is a heat engine. And you can create it just going back and forth just from a source of heat. All right. So I think that'll be it for now.